Alright, so I'm going to do another question to add to our list of example problems. This one is question 60 from chapter 5. So the first step in the list of things to do is to read the question carefully. An impala is an African antelope capable of a remarkable vertical leap. In one recorded leap, a 45-kilogram impala went into a deep crouch, pushed straight up for 0.21 seconds, and reached a height of 25 meters above the ground. So I'm going to write down those numbers. 25 meters, 2.5 meters above the ground. To achieve this vertical leap, with what force did the impala push down on the ground? So we want to find the force, and it's the normal force because it's with the surface of the impala on the ground. Okay. What is the ratio of this force to the antelope's weight? What is the ratio of this force to the antelope's weight? So that's the earth on the antelope. Okay, so those are the two things we need to find. And what do we know? So we know that the antelope, can I draw an antelope? Probably not. Do they have antlers? I have no idea. Okay, so here's the antelope. It's pushing on the ground. And it does that until it leaves the ground. Here it jumps. And it goes up in the air to some maximum height before it falls down again. This is max height. Okay. All right. So there are two parts of this. So there's the part where the antelope is pushing on the ground, and then there's the part where the antelope is actually in the air, rising to its max height. And the first interval is the force interval. So as it's pushing, it's accelerating up and it's gaining speed. And then in the second interval, it's in free fall. And during that time, it's only losing speed until it stops at its max height. All right. So I have my little sketch. I'm not sure that it is, so this is 1, this is 2. We could draw lots more things. So for the pushing part, we probably need a free body diagram. And then in free fall, that's the kinematics part. So let's go back to our list of things to do and check that we've done them. Read the question carefully, yes. Draw a sketch of the situation. Yes, we have a sketch of the situation. Label your positive X direction on the sketch. I guess I'm going to pick up as positive. So let's just put that in somewhere. That's going to be true the whole time. Up is the positive X direction. Underline all values given to you in the text. Associate each given with its appropriate variable label. All right. So we don't know the time of time 2. The time they're giving us is the length of time that the antelope pushes. We know the max height and the mass of the antelope. All right. Decide what variable we're solving for. We need ultimately to find how hard the antelope pushes on the ground. And then useful diagram, solve for acceleration. All right. So we know we're going to need a free body diagram for part 1. So let's do that part first. That's time period 1. The antelope is pushing on the ground, so we have the force, but this should be for the antelope. And I'm calling it an impala. Let's make sure all my language is the same. impala. So we have the normal force from the ground on the impala, and then we have the force of gravity from the earth on the impala. And during this time, the impala is speeding up. In the positive x direction. So we know that the normal force of the ground on the impala minus the force of the earth on the impala had better add up to the mass of the impala times the acceleration of the impala during time period 1. It's really clear this is time period 1. Okay, and then after that, we have time period 2, where the impala rises from its initial velocity, which we don't know, to its max velocity of 0. That's where it stops and starts to turn around. We know its acceleration is minus 9.81 meters per second squared, because we picked up as positive, so this is negative due to our choice of coordinate system. And we know that its displacement during this time is plus 2.5 meters. So this information suggests that we should be using the timeless equation if we need to find something. What are we needing to find? I guess we need to find its starting speed. Let's go back and find its starting speed, because why do we need the starting speed? V naught of time interval 2 is the final velocity of time interval 1. And if we know the final velocity of time interval 1, we can use this equation. Okay, we know the starting, so we know a lot about time interval 1. We know it's the antelope starts at rest. We know the time interval for time interval 1 is 0.21 seconds. We know this. We don't know the acceleration. We're going to need that for our Newton's second law equation. So if we can find this, we really want this, and we're going to find it from time interval 2. All right, so let's see. We want the timeless equation. So for time interval 2, we know the final velocity squared is 2a during time interval 2, the displacement during time interval 2, and this is the initial velocity during time interval 2. So these two things are the same. Squared. I need a squared. Okay, so this one, it ends up at a max height with a max speed of 0 meters per second at peak. So the starting velocity of time interval 2 is equal to minus 2a2 delta x2. And we can plug in numbers for this. So minus 2, the acceleration is minus 9.81 meters per second squared, and the displacement is plus 2.5 meters. So plug all that stuff in, and I'm forgetting the squared. Don't forget the squared, common mistake. Okay, so plugging in all the numbers, we get minus 2 times minus 9.81 times 2.5, and that gives 49. So this whole thing, I'll write it below. So this whole thing is equal to 49, and the units are meters squared per second squared, which tells us that the starting velocity of time 2 is the square root of that, so that's going to be 7 meters per second. Okay. And once we know the starting velocity, as we said before, that's going to be the final velocity of time interval 1, so we're going to plug this thing up in here. I'll solve it below, because otherwise it's too much of a mess. So we still aren't on the assess. Let's just erase this. We're not there yet. We're not there yet. So to quick recap, we used, let's go back to here. We used kinematics, so constant acceleration, particle motion, to find the impala's starting velocity as it begins free fall. This is its ending velocity of the pushing phase. And for the pushing phase, we know that the final velocity is equal to the acceleration of the pushing times the time of the pushing plus its initial velocity of the pushing, which was 0. So the acceleration of the pushing phase is its final velocity divided by the time of that phase. So 7 meters per second divided by the time, which I think was 0.21 seconds. So the acceleration during that time is 7 divided by 0.21, which is 33 1/3 meters per second squared. That has the right units. It's positive, so that kind of makes sense. Right, so that is the acceleration during phase 1. So now we're going to go back and solve for the forces using the acceleration during phase 1. So that's what we just solved for. Okay, go back to solve for the force for the ground on the impala. So I'm going to go back and take my Newton's second law equation that we wrote. And I'm going to solve for the normal force. Remember that we know the force of the Earth on the antelope is the antelope's mass, should be a plus, times the gravitational force constant. And so we can factor out the mass of the impala. Okay, so now plugging all this stuff in, the impala's mass is 45 kilograms. The acceleration during that phase is 33.3 meters per second squared, and the gravitational force constant is 9.8 newtons per kilogram. Remember, newtons per kilogram is the same thing as meters per second squared. So we're going to do the math. 45 times 33.3 plus 9.8 gives me a total force of basically 1,940 newtons. So that is the force of the ground on the impala. Are we done? We are being asked to find the force of the impala pushing on the ground. That's a Newton's third law pair. So it has the same magnitude because they are Newton's third pairs. So that means that Fnig, what we're being asked to find, is also 1,940 newtons strong. It's going to be the other direction, so down on the ground. And then what is the ratio of this force to the antelope's weight? The ratio of this force to the antelope's weight is 1,940 newtons divided by the antelope's weight is 45 kilograms times 9.8 newtons per kilogram. Let's just write that down as a reminder. We do know that. And so 1939.5 divided by 441. So the ratio is about 4.4 times larger. Okay. That's pretty strong for an antelope. And so those are our answers.